Then yes, we will dive into the ocean again. Then thank you for this very nice introduction, because I'm afraid that like often in the ocean, maybe we are less advanced than for the atmosphere. Then you will see that my example and application will be more focused than the general presentation we had just before. Then the idea here is to talk about downscaling of ocean reanalysis. What we have behind, or what is the main idea behind, is that, okay, first, yes, then what we have in the ocean, or in atmosphere too, but also in the ocean, the picture is very bad, I'm sorry, that's, okay. Okay, that doesn't matter, we'll go like, yeah, no, but I don't have HDMI. That's my problem. Okay. Then we have internal to climate evolutions in the ocean. Then this is an IPCC example about the ocean content evolution, or the yes, for example, here in North Atlantic or in other places. And then the idea behind is what is the impact of all this evolution, this long-term evolution, on the global coastal ocean. Then this is an example from Holt and colleagues, which divided the coastal ocean in some subregions and some coastal domains. Then the main idea is what are these impacts, and potentially what are the feedbacks from the coastal ocean to the large scale. Then based on this statement, what I will present you today is, first I will give you my definition, or at least the framework I'm using when I'm talking about downscaling of ocean reanalysis. Why do we need it? And with some illustration and some example. And what are the main limitations of this approach? Because of course you can imagine that we can't do everything that we want. And what's next? Of course, what are the future? Then first, the downscaling of ocean reanalysis. Then when I'm talking about downscaling here, I'm just talking about the downscaling into getting to higher resolution, okay? Then this is an example where we go from 12 of a degree in a subdomain for vertices of a degree. The other part is the reanalysis. The reanalysis means that we are not dealing with 1 or 2 months of simulations. We are more dealing with several years or long periods over we are looking at. The idea is that these regional and coastal domains are interfaced with large-scale and global reanalysis, and it includes, and this is a key point, some coastal or regional processes like tides or rivers that we need to better solve in our case. Then just an important side note before going further is that we are talking today about reanalysis. Reanalysis, you know, that is long simulation with data assimilation. It's kind of interpolation of existing observations, but often we don't have reanalysis, and we are using hindcast runs, which is our large-scale solution. It's the only solution that we have. Then in my talk here, I will include these two family of large-scale run in the presentation. For this downscaling, there are two main approaches. The first one is we do it online, which means that we are running the large-scale model with the small model. And it's kind of one-way or two-way nesting. In the one-way nesting, the large-scale model will force the small domain. And in the two ways, we have or the solution from the small model is influencing the large-scale model. The other approach, which is maybe less expensive in terms of computational cost, is we do it offline. Then we take the output from your previous large-scale simulation or your ocean reanalysis, and then you run it. You run over your small domain. Just to illustrate it, you have here an example about a simulation where they tested the effect of the one-way or two-way nesting. This is domain here in the California current system. Then you have you see the bathymetry here in black. In the small domain nested into the large domain is here, and you see in red. Oh, you don't see very well, but the topography is slightly different because, of course, we have a better resolution in the small domain. When we look at, for example, here an SST sea surface temperature map for this, you see the large domain and the small domain. It's for a given date. This is for the 5-kilometer model inside the square here. This is for the 15-kilometer model inside the square. And this is when we nest one way. When you see when we nested it in one-way mode, you see some discontinuities here. You see the patterns outside the domain and inside the domain. There are not continuity everywhere. Then it's sometimes it will induce some open boundary condition problem in this case, and it's not the best solution sometimes. The other way is to do the two-way nesting, and then in this case you go from the high resolution to the low resolution and the other way around, and then you have a continuity in the structure between both models, the high resolution and low resolution. The other approach, as I told before, is the offline approach. The offline approach here is in another region, close to the Canary Islands. This is a parent model, which is around 8-kilometer resolution, and there is 3-kilometer resolution inside. What we have here is that we are just forcing the model, the larger model, with the small domain with the larger domain. This is for sea surface temperature, sea surface height, barotropic velocities, and relative vorticity. And you see, because you're very familiar now with the one-way and two-way, you see it's the one-way in this case because you can see some discontinuities here, for example, in the velocities, which means that we don't have the feedbacks to the larger domain. Okay, then why do we need to do that? The main ideas behind that is that often we need to solve some higher resolution dynamics. Of course, it's not realistic today to solve all the ocean at the same resolution, solving everything. Then when you are looking at the bay or the river plume dynamics or some tidal, strong tidal effects or some internal waves dynamics, you need to solve at higher resolution. This is one of the first reasons why we need to downscale. The other thing is that when we go close to the coast or in smaller region, you have a bathymetry which is becoming more complex. And with some sharp gradients of bathymetry, you need to adapt your grid, or to have a grid which is adequate for your domain. For example, this morning with a HiCom, we have the most, let's say, the most adaptative solution with some Z-grid sometimes, some terrain following vertical layers in sometimes, and some isopycnal layers for the large scale. Then this is needed for the downscaling in coastal and in coastal regions. Generally, we have at least a sigma following the sigma level coordinates, which is the following terrain, the terrain following coordinates for the coastal region. And the other things is that we have to solve also some processes which have a larger impact in shallow waters. The tides is a good example. In coastal model tides, we have to solve it. It's mandatory. In the global ocean, we just start to solve tides because the first solution was not too bad without it. Then this is for us, which is something which is very important. Then, just to give you some example, it's not exhaustive. It's just a few examples of downscaled applications. Then this is the first one I choose. It's from the Iberia Biscay Island region. It's an example using the Nemo model for a given region. They did some reanalysis over 10 years with 1/12 of a degree and 75 Z coordinates. And it's in open boundary condition. It's connected to the CMM's global reanalysis. Just to show you here some example, this is the middle one is this simulation. Okay, it's the reanalysis, the sea surface temperature. On the left, you have the operational model. What's the difference? In the case of the operational model, you don't have a simulation in this case, and you have higher resolution, 36 of a degree of resolution. What's interesting here is to see that due to a simulation impact, we have some coastal processes which are better constrained, at least for the sea surface temperature in the reanalysis. Let's say here, for example, you have the ocean front, which is a tidal front, which is constrained by the sea surface temperature data. And also you see these patterns here, which is linked to a mixing over the continental slope, and which is which is changing the signature depending what you assimilate as a SST. If you look into at depth, the difference is less important because this is the example for 2 months of the salinity. You see the vertical section here, and you see this pattern around 1,000-meter depth. This pattern is related to the Med Sea water, which is going into the Bay of Biscay, or this is around Portugal and Spain here. And then you see this Mediterranean water at 1,000-meter depth is not easy to reproduce. And maybe you guess the lines here, which is the climatology. And we see that both simulation, then the reanalysis and the operational model, are reproducing quite well this Mediterranean water, which was interesting and good for this simulation. Another example is more focused on the Bay of Biscay. I'm sorry, I'm working on Bay of Biscay. That's why examples are first on Bay of Biscay, but I try to put other examples too. But Bay of Biscay English Channel. This is now from a Mars 3D model, which is a coastal dedicated model. This is 10 years simulation of 1 kilometer resolution with 100 sigma vertical levels. And in this case, we interface, with a hindcast run, which is a Drakkar global simulations. And then what we did in this case, we see nothing. It's the relative vorticity in this case. Then for people who was here this morning, you have a very nice explanation of the vorticity from Julien. But it's the intensity of rotating activities. And what is interesting in this case is that you can see that you have two different regimes in the open ocean and the coastal ocean. And we have a strong seasonality in both places. And sometimes you can see here some lines, then you will see during the stratified months, then back to the summer, which are related to the internal tides or internal waves activities. Then doing this kind of simulation, we solve a lot of processes that we can solve with we don't have in large simulations. Another view about this is, This is from the same simulation. This is the integrated vertical velocity over 150 meters depth, which is an average winter mixed layer depth. You have the corresponding mixed layer depths. And then you see that you have a maximum end of winter each year, which is very regular. And then what's interesting in this work is that you see some differences some years. And that's one of the aim of the downscaling of ocean analysis for us, is that we can infer some internal variability and try to connect it to large-scale patterns or to large-scale features. In this case, what's happening, for example, in 2005, you see these very strong peaks here, is related to a very cold and dry winter. And then we can connect to the heat flux. You can explain by the heat flux this behavior. Just to explain you this figure quickly, this is the vertical velocity times the buoyancy at small scale. Then it's only for scales which are smaller than 40 kilometers. And then at this case, we see this vertical buoyancy flux give us an idea about the instabilities we have in the water column. And then we see that most of the instabilities are in the mixed layer depths, and there are maximum, there is an internal variation with a maximum here in 2005 related to this very strong on specific years. And this is an example of the internal variability, and we can get from these downscaled simulations. Then now, going to another ocean, the California current systems, then you see in this case, they use the ROMS model for long periods. It's 10^-degree resolution. And in the open boundary condition, they use the soda products. This is the model domain. And then, for example, here I just show they counted the eddies in the simulations. And it's interesting because they did a simulation with data assimilation and without data assimilation. And in the case of data assimilation, you see that they get this red curve here. And without the data assimilation, the number of eddies is very small, which means that they don't manage with the own dynamics of the model. They don't manage to have the right dynamics. And the proof is also the green curve when they stop the assimilation in the middle of the simulation, we go back to a small number of eddies. And they go a bit, they went further in the paper, of course, and this is another example where they count the ratio of ageostrophic over geostrophic eddies, which is more to get an idea of the ageostrophic component. The same model, the same simulations, there were also some studies about the upwelling dynamics related to the El Niño events. To reproduce this upwelling dynamics in a local domain like that, we need really to downscale from large-scale simulations. And then this is an example with the vertical transport related to the upwelling. And this is the pycnocline depths. And then you see in red the El Niño events, the blue the La Niña. And then you can see very well that you have a stronger upwelling in this region in the period of La Niña events, and you decrease the upwelling during the El Niño events. And this can be also related from this variable and other variables. They create an upwelling efficiency index or efficacy index, and they relate it very well to the concentration, to the chlorophyll concentration. Of course, when you have the upwelling very efficient, you have more nutrients, then you have more production, then you have more chlorophyll. Then in this case, in Nino events, during Nino events, you have less upwelling, then less production. Then it's very well correlated with the satellite observations here in blue. Another example here is the North Sea, again with the ROMS model, for now the resolution of 6 to 10 kilometers and 32 sigma vertical levels. This is, in this case, they wanted to compare to a coupled climate model. Then it was connected to the global coupled Bergen climate model. And this is very, I don't have to say anything. You see here the Bergen climate model, and you see here the ROM simulation. Then you can see the circulation and the color, which is SST. You can see this is very, very different. Then you see clearly the improvement of getting this high resolution simulation for this domain. Just here, some integrated value was the inflow in the northern part of the domain. And then you see the difference between the black, I don't remember, but the black I think is the ROMS one, and this is the Bergen coupled model one. Then you see the difference of both simulations. Then this is very nice. It seems working very well. We can solve new processes when we are downscaling in coastal regions, but there are a lot of limitations. And these limitations are clearly often due to the boundaries, okay, which is the open boundaries. Then the first is how we can get the large-scale dynamics. And I will go back to one point which was raised by Michel Decay just before. Then the large-scale dynamics. The second point is the atmospheric forcings. Okay, of course we are very constrained by what we put in the atmosphere, but also the bathymetry and the grids problem. I will just talk about these 3 points now. The atmospheric forcings, as we had very nice introduction before, I won't say more about the atmosphere here. Then the large-scale dynamics. Here I just present one solution or one application, but how we can do to keep this large-scale dynamics. And this is what we call the Spectra nudging, which was presented just before. The idea is really to get the low, then the large scale from the larger domain, the parent simulation, and then to keep the model creating its own high resolution, its own small processes in the small domain. Then what we do in the ocean, or in this case, in these applications, we do a free run over a given temporal window. Okay, let's say 7 days. We filter it to reach the scale of the larger model. Let's say it's 10 kilometers. We filter at 10 kilometers, and in temperature and salinity, and we nudge this difference in temperature and salinity with over these temporal windows. Then we correct the large scale, the smoothed field, and then we can then constrain the large scale. This is an example here with a regional model, which is the Mars 3D, and the large scale model is the PSI2V4 model, the operational model. And we can see it very well, but this is the observations in May and October, I think. No, it's not that. No, it's summer. It's summer. July, October. Okay, I thought it was a bit better earlier in the summer, but okay, July, October. Okay, this is the observations. This one. This is the free run with the coastal model. This is the coastal model with spectral nudging, and this is the large scale simulations, which is low resolution. And then what you see here, just for one example here, you see that in the free run, the coastal model, you have an anticyclone, cyclone, anticyclone, cyclone. You see the distribution of the eddies here, which is corrected with the spectral nudging, and we see now it's very similar with what we have with larger domain simulation. Then this is an example about how the spectral nudging has an efficient effect to correct the large scale in our coastal model. The second family of limitation is related to the grid, and two particular aspects. The first one is the bathymetry. Often we don't have it in mind, or I don't know what we have in mind, but we have to take care about that, is that we have the bathymetry from the outside domain, which is generally very smooth, like e-topo bathymetry and so on, which is low resolution bathymetry. And you need to go to a very high resolution. Let's say today we are trying to do some runs with 100 meters or 200 meters of resolution. Then we are looking for very high resolution bathymetry. Then the question is how you connect it. If you just put one with the other one, you will have some steps at the limit, and you can imagine in physics which can create some instabilities or some spurious currents at the bottom. Then this is something which is to be very careful. And then in this example, they just apply kind of transition zone between the open ocean model with the coastal model for the bathymetry. The other point is about the grid, the horizontal grid. And then you have how to connect the child and the parent horizontal grid. And for example, the problem can be for the land mask. This is an example here where you have the land mask, you see the gray cell for the larger domain. You have to connect to the blue cell to the coastal domain. Then you see here again, you need to be very careful, and you can have some spurious problem here, or your interpolation need to be very adapted. And this is another example. Then this is just an example about how it can work. In this case, this is the surface vorticity in the southeastern corner of the domain. And then you can see this is the same resolution. And then you see when we put the high resolution. And in this case, they tried to be very careful about how they did the junction. But you see, they still have some strange discontinuities here that maybe we can go further. Then for the grid connection issues, there are these three main points: bathymetry, the horizontal grid, and the vertical grid. I don't show it, but of course, if you have a Z grid at the open ocean and you have a sigma vertical coordinates in the coastal domain, you need to interpolate. And if we, in the future, I think we could improve it to take into account some conservation issues, because now today we are just interpolating. But if we want to be more precise, we need to take it into account. Then what's next? Just quickly, downscaling of oceanalysis is needed to understand the impact of, let's say, the climate change on coastal and regional scales. As soon as the domain is under influence of large scale. Why I put it there? Because sometimes you're working on a bay, which is where you just have let's say, a canal joining the bay to the rest of the domain. Then you don't need, of course, in this case, to have it very connected. Then the future improvement coming soon, it's of course we need to improve, I think, this part of large-scale circulation in subdomains. How to constrain the large-scale circulation? Spectra nudging is one solution, but it's not perfect at all. And then I think we can go further into this part. The connection also, it's one or two ways, or offline. Offline is computationally easier, but maybe it's better if we do some online simulation, but it's very costful. And then how we deal with that. And then I think the future, and it's what we see more and more in coastal domains, is to go how we connect how we perform coupled simulation in coastal domain, which are coupled with the different interface. The open ocean, okay, we talked about. Atmosphere, you know the coupled atmosphere-ocean system. But there are also the watersheds and the biology, and then how we go to this coupled system and we make an efficient interface with the large-scale simulations. Then that was the message I wanted to tell you today. And then if you have any questions, they are welcome. Thank you.